Hi, I'm Craig Smith, and this is Eye on AI. Terry Sejnowski, an AI pioneer, chairman of the NeurIPS Foundation, and co-creator of Boltzmann Machines, whose sleep-wake cycle has been repurposed in Geoff Hinton's new forward algorithm, talks in this episode about how advances in deep learning, particularly in the scaling of large transformer models, may help us understand our own brains. Terry is a wonderful communicator and makes these complicated concepts accessible to everyone. I hope you find the conversation as interesting as I did. Normally I have the guest introduce themselves. You're certainly somebody that people know, but nonetheless, for uninitiated listeners, give a little bit of your background, and then we'll talk about how AI is developed and what is happening now in deep learning and where you see it going. So, Terry, introduce yourself.
Well, hello. My name is Terry Sejnowski, and I'm currently a faculty member at UC San Diego, where I'm the director of the Institute for Neural Computation. I also direct the Computational Neurobiology Laboratory at the Salk Institute. And my primary field now is computational neuroscience. That is to say, of trying to focus the tools that we've developed here in the NeurIPS community to try to help us understand how brains work, which is a very major scientific problem. Of course, there are engineering spin-offs that come out of that. As we learn more about the brain, that's going to help us create better network models.
And that link to neuroscience between deep learning and neuroscience, can you talk about how the NeurIPS conference developed and why it developed?
The conference grew out of a movement that began in the 1980s, which was actually instigated by physicists and people in computer vision from many different areas of science and engineering, which was a dissatisfaction with the current tools that were available at the time for handling really difficult problems, large-scale problems, things like computer vision, speech recognition, language translation. And one of the things they had in common was that they were very, very high-dimensional in terms of all of the variables and the features. And the traditional tools were based on trying to develop relatively small models. In statistics, you have a small model with a few parameters, and you try to find the optimal set of parameters. We were going in the opposite direction. We wanted to come up with large-scale models that had many parameters, and instead of trying to find the optimal set of parameters, let's find a set of parameters, which didn't have to be unique, but nonetheless gave good performance. So that was our initial impetus, and it kind of snowballed in the sense that our first meeting that was open to the public, we had a bunch of earlier meetings, small groups that got together informally, but it was always self-generated, and we focused on learning. Very early, it became clear that how do you find the parameters? You've got to find the parameters somehow. So by having lots of data and by using the data to gradually improve the performance through optimization was the approach that we took. So the first meeting that we had was under the aegis of the Neural Information Processing Systems Foundation that was founded by Ed Posner at Caltech. And at the first meeting, it was 1987, had a total of 90 submissions, and there were a few hundred people who attended it. And it was really exciting. Why? Because we hadn't been together, that many of us hadn't been together at the same time, and it was unbelievably diverse in terms of where people were coming from. They're coming from math, theory, people from statistics, people from cognitive science, from computer science, from neuroscience. It was like the ultimate interdisciplinary group, and that's very rare, as you know, because we all have these silos that we live in. And each one of the disciplines has its own specialized meetings. But we realized that we were tackling some difficult problems that were common to many, many fields. And so we could help each other by coming together and sharing some of our algorithms, insights, data sets, and so forth. So that was how things got started. Like I said, it was started by Ed Posner, but he tragically got hit by a truck when he was bicycling. And so I was called and asked if I wanted to take over as the president of the foundation. And I agreed. And little did I know where it would go. But it's been exciting to see how this meeting and the workshops especially have grown enormously over the last 10, 20 years. And it's also interesting how it has morphed. So it started out as a focus on models that resembled networks in the brain, Hopfield networks, for example, which were relatively, by today's standards, small networks, but they exhibited some of the nonlinear dynamics that we see in a recurrent network that you need in order to recover complete memories where you're given a little bit of information, you want to complete that, get the entire output out. But it very quickly grew in the sense that many other algorithms were discovered. And as they were added year after year, graphical models, support vector machines, Bayesian networks, they quickly became clear that we had here a toolkit. And that became machine learning as the kind of the central focus. Although, again, these are tools that a lot of people were using and adding to. And then about 10 years ago, a NeurIPS meeting that was held at Lake Tahoe, Geoff Hinton had a paper on which he applied convolutional networks to ImageNet, which at the time was the biggest and best image collection for categorizing tens of millions of images into 10,000s of categories. And the improvement there was so dramatic that it got picked up by the New York Times and a lot of other outlets. And within a few years, computer vision was transformed because of the fact that the performance was so much better than the traditional approach, which was by hand crafting features where performance improved by 0.5% per year. And it was like overnight, 20% improvement. The next year, 10% reduction. And now it's taken for granted, but back then it was really a wake-up call.
That AlexNet and the ImageNet competition, it was kind of the kickoff for deep learning. And the conference has really zeroed in on deep learning, right?
I disagree with that.
Okay.
And I'll tell you why, because if you just go through the posters, you'll discover that there's still a great diversity of algorithms and approaches that are still being explored. And if you really look at the way that the meeting has evolved over almost 4 decades now, there's always been, at any given time, the tool, the algorithm du jour, which everybody got excited about, and a lot of papers came out. I remember support vector machines took over NeurIPS for about 5 years. And it takes its course. That is to say, it's explored, and the limits are found. A lot of applications are solved at various levels. And then something else pops up that was being incubated at NeurIPS in workshops or something, and then that takes off. And then every 5 years, you get a breakthrough in another area. And each time that happens, it's a bigger breakthrough in the sense that it covers more applications and has more flexibility. I see deep learning as just another step along that direction. I think we have a long way to go, a much, much longer way to go. The good example, is transformers, right? So transformers are another form of a neural network, but it's gone from feed-forward to recurrent, these transformers with self-attention. And every time you improve the architecture or enhance it, enlarge it, new capabilities appear, right? And so I expect that to continue. And I think that the space of algorithms out there is infinite, and we're just scratching the surface.
Yeah, that space of algorithms out there being infinite is something I've often wondered how you think about it or people in the field think about it, particularly with regards to neuroscience and this impulse to build a model of the brain or figure out how the brain works or build an artificial analog to the brain. Do you think these algorithms, as in mathematics, they exist in nature and we're discovering them, or do you think that we're creating them?
A little of both. Like the Boltzmann machine was a version of the Hopfield net. We basically heated it up so that it was fluctuating. And from that, we got a learning algorithm with Geoff Hinton. And we had wake and sleep phases during which you gave it data that you were trying to train on, then you let it free run, and you subtracted the two. And Geoff Hinton is coming back to that. So it's still, that concept is still permeating. And by the way, humans also have wake and sleep cycles too, right? But what we're looking for are principles that we can extract from nature. And one of the principles that is probably the most important principle is this principle of scaling. So all algorithms, as you increase the size of the problem, they scale with some exponent. For example, if you're doing some kind of a search and you have to compare all pairs, that goes as n squared with n objects that you're searching, trying to find the optimal one. But the problem is that as the n gets bigger and bigger, 1 million, 1 billion, which is where we are today, then it just runs out of steam. You run out of memory. It's not practical. And most of the algorithms in traditional AI have that problem. And when we started in the 80s, we had tiny little networks. I worked on something called NetTalk, which was text-to-speech. And by today's standards, it had a couple hundred units in it, maybe a few tens of thousands of parameters, weights. But it did something which was really quite remarkable. It took something that is as irregular as English pronunciation, and it learned the regularities and the exceptions. And there are many exceptions, as you know. And so it is an architecture that absorbed all of the complexity of phonology, it's called in linguistics. And that was a shock because linguists at the time were using rules to explain all the regularities. So they had books with thousands and thousands of rules, and with each rule there was lists of hundreds and thousands of exceptions, the whole classes of exceptions like French-derived words. But then within the exceptions there were rules. But then within the rules within rules there were exceptions. You know, it's rules all the way down. And that's a very awkward representation. And first of all, it takes a lot of effort because you have to figure out what the rule is, and then you have to find how to deal with it. So here we go. And now with learning, it seems like we can do both. We don't have to separate it. And it doesn't take labor. That was the big, ultimately, savings, is that instead of a human manual labor, figuring out the rules and working out the details of the features, you could automate that. And that could be applied to any problem. It's not that each domain has a separate set of rules. It's like we could learn them. And now, here's what we didn't know back then. In the 80s, we had these small networks and we had the learning algorithms, the same ones we have today, by the way, but we didn't know how well it scaled. What would happen if you scaled it up by a factor of 1,000 or 1 million? Well, now we know. It turns out they scale beautifully. And this is a principle that we actually had observed in nature. If you look at the size of the cortex of different species, what you discover is that, especially in primates, more and more of the volume of the brain is devoted to the cortex, cerebral cortex that is on the outside. And in humans, it's so abundant that it gets convoluted. It gets all these folds. And so it looks like a walnut from the outside, right? It's that's because you need more surface area. You got to get the same surface area and the same volume. And so how do you do that? And it's very, very rare, even in biology, because most of the other parts of the brain don't scale that way. So there's something special about cortex. More is better. And that's what we've discovered about some of these neural network models, that it scales linearly. That is to say, as you add more units or parameters, it just scales with that number. It's not n squared, it's not n cubed, it's n. Biology has this additional advantage that you can do it all in parallel. In other words, you have n neurons, that's a big number, it's 100 billion, but they're all working together in parallel, which means that it's order 1. Doesn't matter how big your brain is, it's working in real time, or how small. They all work in real time because of the fact that they scale. It's scalable algorithms. So these are the principles we're looking for in nature, is scalability. We're looking for ways to reduce energy. Nature manages to run our brain on about 20 watts. Right? These large-scale computers now that are being used to generate transformers, right? They're megawatts. We're talking about a completely different order of magnitude, 6 orders of magnitude. Everybody knows that, look, we can't continue to scale up. We're not going to get a power plant, a gigawatt power plant. For creating networks, we need to be able to have a technology like the ones that the brain uses for being able to scale within a reasonable energy budget. So that's where we are. We're extracting principles, and there are many others now that we found, similar to what happened, by the way, early in this development of man-powered flight. In the early days of AI, everybody laughed at us because, what are you going to learn about artificial intelligence by studying the brain? What are you going to learn about flight by studying birds, right? Ha, ha, ha. The Wright brothers spent a lot of time looking at how birds glide because somehow, without much power, they were able to go a long distance, right? Well, that's what they were trying to do. And the other thing, they looked The feathers, very light, but very strong, stiff. So they had their plane not built out of metal, but out of wood, spars, with canvas in between. Very stiff, lightweight. So this is how you extract principles from nature and then incorporate it. You have different materials, you have different ways of accomplishing the same thing, but you get inspiration. You have a new way of thinking about the problem. And that's what we're doing with the brain.
On the scaling problem, so there's no end in sight in terms of the improvement as you scale parameters, but there is an end in sight, and I think we're close to reaching it in scaling the power required to run the GPUs.
So it's interesting because what's happened is that there's so many applications and there's so many people using the traditional hardwares. Von Neumann architecture. Trillions of dollars have been put into developing fast and cheap computers using the von Neumann architecture. But now what's happening is that the hardware manufacturers are beginning to realize, oh, we can build these massively parallel networks better, much more cheaply than simulating them on a von Neumann machine. And not only that, but it's less power. So that there's going to be a whole set of generations of hardware that is going to come out, and it's already out there. There's one company that is building a wafer scale, Cerebrus. It has to be water cooled because there's a lot of cores. But the point, though, is that it's much more efficient in terms of power usage and for the architectures that we're using right now. And that will continue.
And more than the hardware, to me, I had a conversation yesterday with a young PhD student about data pruning and different strategies for identifying what you can throw out and still train efficiently. And as you prune the data used for training, you use less power. So that sounded promising to me.
See, what's happened now is that there's like thousands of people out there who are figuring out how to simplify, how to reduce the training time or the training set. There's a very powerful method called distillation, which is interesting. So it turns out you need a huge network and a huge amount of data to train it. But once you've trained it, you can now take the input and the output of that complex network and use it to train a much smaller network. It's called distillation. And you use it to train it not just on the correct output, but on the probability distribution of the output. And you can come pretty close to having the same performance for much less hardware. What that's telling us is an important principle, which is that maybe why we have such a huge brain is not performance. It's for learning from this huge amount of data in the world. But once you have distilled it somehow, you can now run it really fast with much less hardware. And that opens up new resources in the cortex for learning new things. There's actually evidence for this, which is really a mystery for neuroscientists. It's called drifting representations. So it was always thought that, well, if you have a neuron, you're recording from it someplace in the visual system, that it has some feature that it responds to, like a line, vertical line, that will be there fixed forever. It turns out, interestingly, that now we can record over long periods of time, for weeks, for months, and we discovered that, oh, the feature it responds to changes. It's no longer vertical. Now it's some other angle or some even more complex stimulus. And that's called drifting representations. And what is that telling us?
The feature changes or its location in the brain?
The same neuron is tracked optically over many weeks and months. And if you just do the same experiment over and over again, you discover that you get a different answer every time, over time. And that has shocked us because it's a very different view, because now it means that the cortex is not fixed piece of hardware like a digital computer, right? Where each transistor has a function and it's going to stay that way, right? Unless it breaks. No, it's the whole brain is shifting all the time. It's malleable. It's adaptable. As the environment changes, it shifts. But it takes time, right? It takes changes occurring over times that are long enough so that you wouldn't notice it. If you're just doing a single experiment or just a few experiments, you'd have to monitor it. So that's a big shock. And now we're beginning to think that, gee, this is one of the problems we have with these networks. You train them up and you use them, but they no longer learn, right? So you need something called lifelong learning. Well, our brains do lifelong learning. Maybe this drifting representation is an indication of how we do that. So this, again, we're extracting a principle from something we've observed in the brain, and that could generate the next generation network that based on similar principles.
You said that Geoff Hinton is bringing back Boltzmann Machines?
Okay, so first of all, let me tell you the history. The history there was that my background was in physics and neuroscience, and his was in psychology and AI. So complementary, and we just hit it off. We were at a small meeting, 1979. It was a workshop at San Diego. And we both had the same beliefs about how nature was the only existence proof you could solve difficult problems like vision and speech and language. So we should be looking carefully at how nature solved those problems and trying to understand that in a way that I was telling you about the Wright brothers, although we weren't thinking about the Wright brothers back then. But it's clear that this is something that has happened over and over again in history. Right? And we came across, like I say, through the Hopfield net, heating it up and looking for learning algorithms, we came across this principle, which we call wake-sleep. In other words, you have two phases. One phase is when you expose the network to the inputs and outputs of the task you're trying to solve, and then you let it go and then let it free run. Now, why should the Boltzmann machine learning algorithm need to do that? And here's the reason. The trouble is if you're a neuron somewhere in the middle of the brain or a unit in some hidden layer, and you're getting correlations coming in on the inputs, you have no way of separating out whether those correlations are due to the outside world, the task itself, or some other neuron, internal correlation. And so the danger is that if you run it without any sort of way of canceling the internal correlations, then the brain, the network will basically spend more and more of its resources. The weights are going to be focused on internal correlations, and it'll ignore what's coming in from the outside. We call that folie à deux. People start self-referencing. The beauty of having the sleep phase is that that will be purely generated by internal correlations. So you subtract that off. Now, this is the principle. Like I say, it's a principle that came out of the Boltzmann machine. Now, Geoff has discovered how to use the same principle for feed-forward networks, a very elegant, very beautiful approach, which is competitive with backprop and also much more biologically plausible. So that, I think, is going to be a real advance, both in terms of the way that we think about learning, because the backprop is extremely heavy-handed. You have to have information going backwards over connections. You have to be able to hold on to the state of the network on the forward pass. So those don't exist in the brain, but it's very efficient. It's very efficient, and it has proven to be scalable, so it's universally used. However, if nature has found a way to do that without the heavy hand, and it does it with wake-sleep, and we do, after all, spend a lot of time sleeping, then that's a big win. And also, it may help us understand how the brain works. So this is another step along the way toward a better understanding, new versions of old algorithms that we can build on. Again, it's the first step. He'll be the first to admit that he's focused on small problems, relatively small problems, in order to be able to make progress. But there'll be many, many ways of building on that.
That's fascinating. Could you use this forward network in a model the size of GPT-3 or?
I suspect so. He hasn't demonstrated that yet, but I don't see any problem with applying it to that kind of architecture. In fact, it is a feed-forward model for inference. And so he's showing now you can do the same thing with learning, a feed-forward learning model too. So, never know. I mean, when something is new, you have to explore it. It could lead you in many different directions, but it smells right. From my background and training, I can see how it could be implemented in the brain. It doesn't violate any principles. And also, many people have tried to come up with versions of backprop in the brain. There's dozens of papers, and none of them are as successful as Geoff's version. That's a good sign. It's a good sign because it means that this may be the roadblock, right? There was a roadblock. And by the way, the last time this happened was back in 1983 when the perceptron learning algorithm that was introduced by 1959, Frank Rosenblatt, and it's a beautiful, elegant, simple learning algorithm for a network that just has one layer of weights between the input and the output. And Minsky and Papert studied it mathematically and came to the conclusion that it was very limited in terms of what it could represent, namely linearly separable functions, which is to say ones for which if you have a space the dimensions of the units, you could find a plane running through it that separates the positive and negative examples, right? Those are the weight space. And in this paper, I point out it's a real strong limitation, right? And they thought that there wouldn't be, in their view, any learning algorithm that could generalize this to a multi-layer perceptron with hidden units. And that's fair enough. I mean, that was their opinion. But others who read the book or didn't read the book got the impression that, it's been proven that this is a dead end. And so I remember when we were starting out, we were told continually, don't you know that it's impossible? So why are you even bothering, right? This is like 20 years where this really elegant beginning was not pursued. And that's where Geoff and I came up with the Boltzmann machine, and Dave Rumelhart and Geoff came up with backprop and many, many others. I mean, it really exploded. That's what was so exciting about the 80s, was that we were making these discoveries. And so that's an example of where there's a bottleneck in thinking, where it just stopped a whole generation, literally, from making any progress because people had believed something that was wrong. And now there's this bottleneck having to do with brain can't do backprop, right? So it's a dead end. And now what Geoff has done is yet again shown that, there's a way of getting around that. And just by switching the architecture around a little bit and incorporating some old ideas from the Boltzmann machine, we can make progress. And so that's the way history progresses in these paradigm shifts, right? You go from one to another. You don't solve all the problems, but you're on a different level. And what you do is incremental improvements to get better and better and better and better. And that's what's happened over the last roughly 20 years, 30 years, is incremental improvements, more computing power, more data. But those are just incremental, right? We can see how that was going to progress. But when you get with these jumps, but Transformer was another jump, then it's a whole new ballgame. You have a whole new set of tasks, applications, things that you didn't expect. And I think that'll continue for a long time. I mean, that's the way it's always all through science.
Whether or not it's this new forward algorithm or it's scaling the Transformer, it's mind-blowing how much has happened in 5 short years.
Or even less, actually, the last 3,
Yeah, since GPT-3.
I've written an archive paper on this, and the title is Large Language Models and the Reverse Turing Test. So here's the insight. I was reading an Economist article on large language models, but at the end, the author said, I have to give credit to GPT-3 that helped me write this article. And it came along with 2 interviews, one by Blas Diarca and the other one by Douglas Hofstadter. And they were diametrically opposed. One of them came to the conclusion that it has a very sophisticated understanding of theory of mind and social interactions. And then Douglas Hofstadter said it was totally clueless. It had no idea what was going on. And I'm not going to go into the details except to say that when you get something that is so different from 2 experts, right, it means there's something interesting here. And so I started playing with it myself, and I came up with the following conclusion, that it's pretty clear that it's been trained on a huge amount of data from many, many different people, things that range from short stories, technical reports, poems, computer programs. I mean, it's just endless, right? It's just huge from the internet. And as a consequence, it doesn't have persona. It's not like us. You have a certain personality. It may change a little bit over time, but it's different from mine, right? And we all have our own personalities, our own personas. But what it can do is very interesting. It can adopt any persona, depending on how it's primed. You can ask it to be a persona. You can ask it, or it'll just pick up your persona. So what was happening with the interviews is very interesting, is that if the person it was talking to is very highly intelligent, knew a lot about social interactions and theory of mind, and was being given a story about that, it immediately picks up on that and it raises its level persona to match that. But if someone's interviewing it with nonsense, things that don't make any sense, what's it going to do? You ask a nonsense question, you get a nonsense answer. That summarizes Doug Hofstadter's interview, right? So it's called the reverse Turing test. That is to say, instead of the human trying to detect whether an AI is human or not, the AI is testing the human for how intelligent the human is.
Excuse me, Terry, just a minute. Come in.
Mr. Smith, your tea is ready.
Beauregard, I've told you when the light is on in the tower, I'm recording.
Apologies, sir.
Sorry about that. Where do you think this scaling, whether or not it's with a more efficient algorithm, is likely to go? And you referenced the Wright brothers and birds a few times, but the Wright brothers didn't build a bird. They built an airplane that did something like a bird, but it's very useful. I mean, AI doesn't have to be an artificial brain, but it's something that is extremely useful.
In fact, that's the point I'm making in my archive paper, which is that there's this huge debate that's raging. Does GPT-3 understand what it's saying? Is it intelligent? Some people think it's just a parrot, a stochastic parrot, which is very easy to dismiss because there's no way that it's just replicating something that is out there, because you can ask it questions that have nothing to do with what's out there, and it can generalize. That's the essence of a neural network, is it generalizes from a relatively small number of examples to data that's never seen before, but from the same probability distribution. The networks have to be able to absorb a tremendous amount of data, information, and they got to extract. These hidden units have to be able to distill what are called latent variables. That is to say, things that are like concepts. For example, if it was being trained on faces, the concept that you have two eyes and a nose, right? Something that is common to all faces. It has to represent that and the relationship between those features, right? And that is a way of compressing all the data and extracting what's regular and statistically significant. And so language has only been around a few 100,000 years. It's something that evolved. And there's not a whole new brain area called language, right? It's embedded in the existing sensory motor structures in the cortex and in the basal ganglia that generates motor sequences. So maybe what happened over evolution was that humans, through social interactions and being driven by the value of being able to communicate, became large language models embedded in a primate brain that was around and had all kinds of fancy stuff in it for sensory motor interactions. And here we are, right? So maybe it's telling us something about ourselves.
Yeah, I've had kind of a similar conversation a number of times in the last year. Everything I say to you and everything you say to me is kind of an accrual of everything that you've read and everything that you've experienced and seen, and your brain knits together
some high-level understanding, which then is used to generate new sentences, right?
And the semantics of the word reasoning aside, maybe we're just language models that are, whether you want to call it mimicking or what, that's processing and integrating.
No, this is not to demean humans, right?
Sure.
These are tiny, by the way, compared to the human cortex. So, as I say in my archive article, one thing we know for sure is that they're not human. Whatever they are, they're something different from human. But what's really interesting is what I think the impact is going to be on philosophy. It's already clear that philosophers are very, very interested. In fact, at the end of my archive paper, I present an interview with philosophers, and not too surprising, GPT-3 sounds a lot like a philosopher. But if you ask, what's the definition of these words, right? Consciousness. Well, you go to the dictionary and it has a bunch of other words and you look those up. It's all circular. There is no real definition. And same is true of intelligence, understanding. All those words are ones that we use in a colloquial way, and we kind of understand what you mean by consciousness because we experience something. But if you want to study it scientifically, you're in trouble because it's just hard to figure out some more fundamental level, like in physics, right? We have theories that explain the properties of matter. And long before physics or chemistry, we had words for it, right? We had phlogiston was a word that was supposed to represent fire. Some substance that comes out of the wood, right, is called phlogiston. Well, now we understand physics, we understand combustion, we understand the oxygen, so we have a theory. So what I think is going to happen over the next, who knows how long, decades, is there will be, from understanding transformers and these large language models, we may actually come up with a real theory
of consciousness
for all of these words, to the extent that you can find them in these networks. Well, for one thing for sure, we're going to figure out linguistics, right? Because one thing you can't deny is the fact they're talking to us. Not even Gary Marcus denies that, right?
And that would argue then that at some point, with enough scale and maybe tweaking algorithms, that you actually will be able to build a system or a network of systems that approximates consciousness.
So listen very carefully to what Dave Chalmers told us. What he told us was that it's not a binary decision if you're conscious or not. It's a gradient, it's a spectrum, and there are different kinds. Animals, dogs have dog consciousness. Whales have whale consciousness. And he talked about fish. I'm not sure about fish, but they have their own version of consciousness. And they're all different, and they're all adapted to whatever their environment is and their social structures. And so why not these large language models, that they have a different kind of consciousness from all the rest of us and all the other species. It's just a different one. But the real difference is that we can go in and examine it. We have access to every single unit, every single weight, every single activity pattern for every input, right? And it's open. It's a function. It's a mathematical function. This is not a mystery here, right? Mathematicians know about functions. They can help us. They should be able to help us understand what mathematical theorems or approaches, tools are needed to extract from that complicated network that we created, how it works. And that will give us some clues.
So these models will teach us about what consciousness or intelligence is, but they also will attain some form of consciousness or intelligence. Just look at what's happened, as you said, in the last 3 years. If we can continue to have that kind of progress.
You're right. I mean, that's the part that is so unpredictable, is that if we've made that much progress in 3 years, where will it head? And I've given you one scenario, is that we'll be able to dissect it and understand it mathematically. That's one scenario. Another scenario is, instead of having to type in a keyboard, you'll be able to talk to your computer and it will understand you. Even things like automobiles, be able to talk to your automobile. It's a universal appliance that will be taken for granted. 100 years from now, people won't even remember a time when we didn't have them talking to us. It'll just be taken for granted.
That's it for this episode. I want to thank Terry for his time. If you want to read a transcript of this episode, you can find one on our website, EyeOnAI, that's EYE-ON.AI. We love to hear from listeners, so I encourage you to email us your thoughts at Craig@EyeOnAI, that's CRAIG, at EYE-ON.AI. We have listeners from all over the world, and I'd love to hear from whomever is listening in Nepal, for example. I see several of you show up on the map of listeners. In the meantime, remember, the singularity may not be near, but AI is about to change your world, so pay attention.